everyone. My name is Elias. I use they, she pronouns, and I have the pleasure today of introducing the speaker for today's event, who happens to be my supervisor, Dr. Richard. Richard received a PhD in logic and the methodology of science from the University of California in Berkeley in 2001. He has taught at the University of Calgary since then, and he's held visiting appointments at UC Irvine, McGill, and the University of Paris. He works on technical issues in mathematical logic, especially proof theory, and also on the philosophy of mathematics and the history of logic. He's the author of numerous articles, as well as co-author of the book An Introduction to Proof Theory, as well as one of the editors of the collected works of Rudolf Carnap. Additionally, Richard is a founding editor of the Review of Symbolic Logic and the Journal for the Study of History of Analytic Philosophy, and is an associate editor of Studiae Logica and a subject editor for the Stanford Encyclopedia of Philosophy. Today, he will be speaking to us about the applications of logic in computer science in his talk titled Surprising Connections, Things Computer Science Learned from Philosophy.
Thanks, Les, and thanks, Clifton, for having me. So, who here happens to be a computer scientist? And who happens to be I guess I know all the philosophers. So, who has heard of logic before? Okay. So, what I'm going to talk about is two examples where logic is applied in computer science. And that is not the surprising thing, right? So logic is very useful in lots of areas of computer science, but what's perhaps surprising is that the particular kinds of logic and the particular methods that are used in computer science go back to the work of philosophers, mainly in the mid and late 20th century. The two examples I'm going to talk about are the automation of reasoning, so automated theorem proving, or automated reasoning in general. And the second one is automated verification of protocols, circuits, programs, generally systems, right? So systems that computer scientists care about, and they're writing programs that deal with these kind of systems, right? And before I do that, I'm going to just give you a thumbnail sketch of what formal logic is about, just in case you don't remember what you learned in your first year logic course. So the philosophy department here teaches Philosophy 279, Logic 1, and it's a required course for all computer science majors. So we teach this stuff to fledgling computer scientists, 700 of them every year. So thanks, keeps us, that's where our money's money. All right, so logic. So when we talk about logic, or at least the logic that's applied to computer science, we talk about formal logic, and formal logic deals with inference and properties, inference between and properties of formulas or sentences in formal languages. There are two that are taught in Logic 1 and that are most widely used. The first one is propositional logic, and the second one is predicate logic. So I'm just going to give you a couple of examples. I'm not going to give you the whole definition, sequence of definitions and stuff like that, right? So there are two kinds of things that logicians are mainly interested in when they talk about the properties of logical systems, or what they study in the first place. And the first one is inference or reasoning, correct inference. And the second one is properties of collections of sentences. Maybe you think of collections of belief, right? So in the inference part, what we're interested in is whether, assuming certain sentences are true, do certain other sentences follow? Are they also true by necessity? So that's correct inference. And the second one is, are a bunch of sentences together consistent, right? Do they contradict each other or not, right? If they contradict each other, then that's bad, right? So for instance, if you're thinking of a set of sentences that describe all your beliefs, you would like to not contradict yourself. You would like to have consistent beliefs. And so testing or having an account of what it is for a collection of beliefs to be mutually compatible, that's another important thing to have an account of, to have a test for, and so on, right? So let's look at a couple of very simple examples. So the first example is in propositional logic, right? So an inference might go from two sentences or assumptions or beliefs. Let's say the first one is Socrates is human. The second one says, if Socrates is human, then Socrates is rational. And you can guess what we can conclude from this, or what follows from this immediately. It's that Socrates is rational, right? Why is that? Well, it's an inference that can be formalized in propositional logic by taking certain parts of these sentences, such as Socrates is human and Socrates is rational, and representing them by single letters, lowercase letters, like H and R. We call these propositional variables. And they stand for the propositions or the sentence Socrates is human and Socrates is rational. And once we formalize it, once we symbolize it the way I have it here on the right on the slide, H arrow R, therefore R, right? If you are reading this arrow as the conditional if then, right? Then you sort of like, I don't really have to explain a lot for you to believe that that's a correct inference, right? Because that's just the meaning of if then, right? If then means if the first thing is true, then the second thing is also true. And if your first premise is that the first thing is true, well, then the two together give you that the second thing is true, right? So that's correct inference. This particular inference is called modus ponens, right? And logicians, what they do, or like mathematical logicians, right? They do two things when they're studying a system like this. The first one is define a proof theoretic a system that allows you to, for instance, derive conclusions from the premises that you have, right? So a proof theoretic system would, for instance, allow you to go from these two assumptions, H and if H then R, to R using a number of very simple rules of inference that are they're purely formal, right? So you don't have to understand what the sentences mean. You just sort of pattern match and get to the conclusion, right? In this case, the inference rule that would be used looks just like this, right? So the inference rule that goes from H and if H then R to R is one of the oldest inference rules that logicians have proposed and studied. It's called modus ponens, right? Then the second thing that logicians do is give semantic accounts of why this inference is good, right? And the semantic account has to do with things like truth and falsity, right? So a semantic account of why this inference is valid would say something like, well, these letters stand for things that can be true or false. These are the only two possibilities. And if the first thing is true and the second thing is also true, then that rules out the possibility that R is false, because then you would have a conditional if H then R with a true thing on the left and a false thing on the right. And that's the prime example of where an if then statement is false, right? If the if part is true and the then part is false, then we would deny that the if then statement itself is true, right? So that's sort of the semantic account. And for propositional logic, there's a very simple procedure to sort of mechanize that, and it's the method of truth tables. I'll show you one in a second. Right, but I said there are two things that logicians do. The first one is inference. The second one is whether sentences together are compatible or consistent. And logicians also like to talk about satisfiability or unsatisfiability. So if sentences together are compatible, we would say that they are satisfiable. Just as a matter of terminology, right? And here you have three sentences, for instance, that are not compatible, that are therefore unsatisfiable, right? The sentences together are Socrates is human, H. If Socrates is human, then Socrates is rational. If H then R, and Socrates is not rational, not R. Right? And again, right, so you would have two methods to test whether that, or to show that these sentences are incompatible, or to test whether these sentences are compatible. The first one is proof theoretical, right? The proof theoretical would take the first two sentences and use modus ponens to derive R from it. And then you have R, but you also have not R, right? And that's a direct contradiction. And then you know that your sentences are mutually incompatible and are unsatisfiable, right? And the semantic method would look at all the possible ways that H and R can be true and false. And if it turns out that all these possible ways make at least one of these sentences false, then they can't be true together. And then we say that those three sentences together are unsatisfiable. Right? So I said, right, so the semantic method is truth tables. It works perfectly for propositional logic. Incidentally, it was introduced by a philosopher, Ludwig Wittgenstein, in his 1920 book, Tractatus Logico Philosophicus. And the method of truth tables is, as I already mentioned, right, it's very simple. It's basically a table that lists all the possible ways for the letters, the individual letters, to be either true or false, because we say those are the only two possibilities, right? So if you have two letters, H and R, then there are four possibilities for them to be either true or false. And then if you have a single sentence, for instance, this is just sort of a sentence that describes the reasoning step in the first example, right? It says if H and if H then R, right? So it's a more complicated sentence. It uses another symbol, this ampersand, right? So this stands for and. H and R is true if both H is true and R is true, and otherwise it's false, right? So once you know whether H is true or not and R is true or not, then you can just compute using some individual truth tables for the and the arrow, what the truth value of the entire sentence is. And in this case, it's true, right? So if H is true, and if H then R, and the H is true and the R is false, then that arrow is false. So you have true and false, that's false. And then you have false, arrow, false, and that's true, according to the truth table for the conditional. All right? So this is how truth tables work. And for computer science applications, it means that this is a very simple algorithm for testing whether an inference is correct, whether a bunch of sentences is satisfiable together, right? You just do the truth table and make sure that there's T's all the way down. That tells you that the inference is correct. Or if you want to know that a bunch of sentences are mutually incompatible or inconsistent, then you do the truth table for all of them. And if it's F's all the way down, then at least one of the sentences must be false under every truth value assignment, as we say, right? So in this case, right, so this truth table here shows that the sentences are mutually compatible or unsatisfiable, right? And if there's one true, then this collection of sentences is satisfiable. So it's a very simple method. It works just by enumerating all the possibilities. If there's finitely many letters, then there's finitely many possibilities, and you just write a computer program that checks for each one of those possibilities if your sentence is true, and if it's true for all of those possibilities, then the inference is good. And if you find a possibility where the assumptions are true and the conclusion is false, then you say the inference is bad. Right? All right. So that's propositional logic. Very simple method for testing whether inferences are correct or sets of sentences are compatible. The more interesting, more expressive language that logicians study is predicate logic. And predicate logic adds to the so-called connectives of propositional logic. So the if-then arrow, the ampersand for and, there's also symbols for or, and if and only if, and so on. Adds the ability to talk about objects. So there are terms for these objects. So in our example here, for instance, the first sentence, Socrates is human, is now symbolized H applied to S, and S would be a name that picks out Socrates. And the H is a so-called predicate symbol, and it picks out a concept or a property. So in this case, it would pick out the property of being human, right? So to formalize Socrates is human, you say, well, let's introduce a predicate, being human, and introduce a name, S for Socrates, and then the sentence H of S or H applied to S says, Socrates has the property that H picks out, so Socrates has the property of being human. And we would introduce a second predicate symbol R for being rational. So R of S would say that Socrates is rational. That's the conclusion of this inference here, right? But we've replaced the second assumption, if Socrates is human, then Socrates is rational, with a more general claim, namely that all humans are rational. And that can be symbolized in predicate logic by a combination of the conditional symbol with this upside down A, which is called the universal quantifier. And it says everything has the following property. Every X has the following property. And what is the property that every X has? If X is human, then X is rational. And that's one way of saying that everything that's human is also rational, or all humans are rational. Right? So that adds a whole bunch of expressive power because you can talk about objects, you can talk about properties. You can also have more than one argument, so you can talk about relations between objects. If you have, L of S and T, for instance, right? Then that would say, I don't know, S is S lived longer than T or something, right? So some two-place relation. You can also do three-place relations and so on, right? So this turns out to be very very powerful, and it took a long time to get to this place. So logic is one of the oldest disciplines, probably. I mean, it's probably almost as old as philosophy itself, and philosophy itself is probably the second oldest discipline after mathematics, probably, maybe even older, right? So this started in the 25th or the 4th century, 5th century BC with Aristotle and Chrysippus a century later, and then for 2,000 years, people were thinking about the kinds of canons of correct inference that the Greeks had proposed and amended them and expanded them and so on. And then in the 19th century, mathematicians became interested in logic and in the symbolisms and developed symbolic logic. There were, a bunch of people whose names you probably know. For instance, George Boole of Boolean logic, and who was a mathematician, sort of applied algebraic methods to the study of propositional logic. But the kind of logic that we deal with, predicate logic, that's used to formalize, actual reasoning in mathematics and computer science and so on, is due to a bunch of philosophers, right? The two who worked on this who pioneered this in the 19th century were the American pragmatist Charles Saunders Peirce, who invented predicate symbols and relation symbols and quantifiers, and the German mathematician / philosopher Gottlob Frege, who basically did the same independently of Peirce, but also developed the first proof systems for predicate logic. In fact, it wasn't just predicate logic, it was an even more expressive system of logic, higher order logic. And he didn't just develop the formal language for this and the proof system for it, but also applied it to formalize mathematics in an effort to reduce all of arithmetic, all of number theory to purely logical principles. And then in the case of doing that, right, so he thought long and hard about what truth values are, what predicates are, how language works, how the meanings of sentences are determined by the constituent parts of the sentences. So he sort of introduced compositionality as a principle. For all of these reasons, right, so Frege is taught in every philosophy of language course, in every metaphysics, contemporary metaphysics course, and he's generally considered one of the fathers of analytic philosophy. And then the third guy here is Bertrand Russell, who was a leading British philosopher who worked from about 1900 to his death in 1970, and he started out as being very interested in philosophy of mathematics, in particular geometry, and he continued Frege's work for the formalization and systematization of mathematics using logical principles. And he is basically responsible for the symbolism that we as logicians use today. And together with his teacher, Alfred North Whitehead, another Cambridge philosopher, early 20th century, wrote a 3-volume huge work called Principia Mathematica that sort of developed logic from predicate logic all the way through the formalization of geometry in logical systems. So with Russell's Principia Mathematica, we really have the symbolism and the proof theory of predicate logic well developed. There were a bunch of people coming after Russell, of course, who took up research in mathematical logic that includes philosophers, includes mathematicians. But I'm gonna, in the interest of time, I'm gonna skip my 4-hour lecture on the history of logic in the early 20th
Doors are
century.
locked.
All right, so this is how we got modern logic. And this sort of ends in the 1910s, right? So there's a whole bunch of stuff that happened until 1930, including, for instance, different kinds of proof systems. Kurt Gödel's work on the completeness of predicate logic. But I'm going to skip over that and get to my applications, right? So the first application, as I promised, was automation of reasoning. And of course, automation of reasoning only really becomes a question when you have things that you can use to automate it, as opposed to doing it by hand or doing it sort of on paper. And so that brings us to computer science, right? So in computer science, computer scientists deal with algorithms and systems that describe and algorithms that answer questions about various things. And one of the things that they would like to do, or that they do, and one of the earliest things that that people working with computers were trying to do, right? Like the first thing, of course, was breaking codes. The second thing was calculating trajectories of missiles and stuff like that, right? But then once the Second World War was over, right, now all of a sudden you have these electronic computers, and it seems like, you know, we should be able to do more things with them than calculate rocket trajectories. And one of the first things people were thinking, well, you know, can we teach them to think, right? So AI was born in the 1950s. And one of the first things that people did in, I think, 1956, right, was write a computer program that proves things in logic in Principia Mathematica. That is the Logic Theorist by Newell and Simon. Right, it's one of the earliest, like basically the birth of AI. Right, it's not the earliest actually implemented theorem prover, but it's close, and it's the first one that's sort of generally proving things in logic. Right, skip to today. Right, so nowadays, questions of logical questions about various kinds of things happen all over the place in computer science, right? So, for instance, mathematicians are interested in automating the verification and the finding of proofs in mathematical theories. You can use it for reasoning in scientific theories. And computer scientists use it for less heady things like reasoning about programs, making inferences from knowledge bases or data sets and things like that. These things are also called ontologies. I'll give you an example in a second. right? And the kinds of questions that you need to answer about these things are logical questions. Namely, first, what follows from the information that I have, right? So what can I conclude? And the second thing is, are these things together compatible? Are they consistent? Are they satisfiable, right? So these are logical questions, and it sort of seems natural to say, well, let's use logic to write down all the knowledge we have about this domain, that where we want to answer some questions. Let's use a logical language to do that, and then use methods of logic to prove things from it, or show that they are mutually compatible in the first instance, right? So we want to use computers to answer these questions. So I mentioned knowledge bases or ontologies. Here's an example from the field of medicine. SNOMED-CT is a very large knowledge base or ontology about basically everything that the medical profession deals with, right? And it has it's mainly consists of rules like the one on top. This particular rule is the rule in SNOMED-CT that defines what bacterial pneumonia is, right? So bacterial pneumonia is a bacterial infectious disease, first of all. It's also an infective pneumonia, and then it stands in relations to two things, namely, it has a causative agent, bacterium, and it has a finding site, namely something in the lung, right? So this is sort of the syntax that SNOMED-CT uses itself. But if you are familiar with predicate logic, it wouldn't be too hard to figure out a way to translate that into straightforward predicate logic. And I've given you an example here, right? All the concepts like bacterial pneumonia, bacterial infectious disease, infective pneumonia, and so on, right? So those will be concepts, so one-place predicate symbols. And then the relations like causative agent and finding sites, those will be two-place relations, right? So they relate the things that are bacterial pneumonias to the other things, namely bacteria or lungs or things in the lung structure, right? So you can write this knowledge definition in predicate logic by saying, well, for every x, right? So every x that you might want to be talking about, right? So that something is a bacterial pneumonia, right? It's the illness or the illness that you find in this particular patient and on this particular site and so on, right? It's a bacterial pneumonia. If it has two properties, namely it's a bacterial infectious disease and it's an infective pneumonia, and there are two more things that this thing stands in relation to. The first one is a bacterium, and X stands in the relation of having as causative agent to that second thing. And then the other thing that has to exist is something in the lung structure, so a part of the lung, and the relation that X has to stand in with that other thing is having as finding site, right? So this is an example of one of the knowledge rules in SNOMED-CT. SNOMED-CT has 1 million of these, and it has over 300,000 predicate symbols, right? So if you want to ask a question, let's say, I don't know, what do I treat this bacterial pneumonia with, right? SNOMED-CT will have the answer, right? So there will be some other things, like for every medicine or every possible treatment, like, I don't know, applying oxygen to the patient and so on, right? There will be a thing, there will be a rule like this, and we'll say, which kinds of diseases it treats, but it won't list explicitly all the diseases it treats. Like if you have a broad spectrum antibiotic, for instance, right, it will treat every infectious disease that's caused by bacteria, right? But it won't say that in particular it treats bacterial pneumonia. That's something that you have to infer from this, together with the information that broad spectrum antibiotics treat all bacterial infections. Right? So these are the kinds of questions that you want to have a system, like a program, where you can ask, what do I treat this? What is this thing? What do I treat it with? And it will make these inferences, right? Of course, you'd also like to test that SNOMED CT is compatible. There are no inconsistencies in it, right? It doesn't say this thing is a bacterial infectious disease, but it's also a viral caused by a virus, right? So those two things are incompatible. There's probably a rule that says that, right? And you want to make sure that that doesn't happen, because once that happens, inference breaks down. Okay, so an example of an ontology, right? And the kind of reasoning, the kind of answers that you want to obtain automatically using a computer system, and that takes us to automated reasoning, right? So automated reasoning would be applying the tools of logic to answer questions like, what follows from this? Are these things compatible? And there's, of course, a prima facie challenge, namely complexity, right? I already mentioned that the practical applications here have huge numbers of sentences that are involved and huge numbers of predicate symbols involved, right? 1 million sentences, 300,000 predicate symbols in SNOMED CT. So if you want to prove something from it, you can't do that by hand, right? So you need to do it by a computer. The problem is that we know that even for propositional logic, we don't have a better, in principle, we don't have a better algorithm than the truth table method for testing whether something follows from it. And as I mentioned earlier, the truth table method is not very efficient because it requires exponentially many lines that you have to check, right? If you have n propositional variables, it's 2 to the n lines that you have to check. So it's exponential. And if you find a better algorithm, then you have solved P versus NP, one of the major unsolved problems in computer science. And it's worse for predicate logic. For predicate logic, there is no algorithm that does it, right? That is a celebrated result by Alan Turing and Alonzo Church from 1935. The question of whether a sentence follows from some other sentences in predicate logic, there's no algorithm that always gives you the right answer, right? But what we can hope for in both cases are algorithms that, for a large array of cases that appear in practice, we can get an answer in reasonable time, right? So that's always what computer scientists always do, right? So there's always things that are very hard or impossible to do, and then they come up with algorithms that in practice work reasonably well or approximately well, right? And that's basically the question that logicians and sort of the earliest people working in the AI asked themselves in the 1950s. So now, how did that happen, right? So what had to happen in order for us to know how to make computers reason practically, right? And here, this is where a bunch of philosophers laid the groundwork. Giving you some pictures here of just some of the people who were mainly involved in this. The first one is Van Orman Quine. Quine was possibly the most influential American philosopher of the mid-20th century. And he had a sort of an early and enduring interest in logic. So he actually developed his own set theory, his own logical system. Computer scientists know him from the Quine-McCloskey algorithm for simplifying circuits. And he proposed in 1955 to use a result from proof theory by a French mathematician named Jacques Abraham to use this result as a proof method for predicate logic. And then Two other people. This is Martin Davis. He wasn't, I guess he wasn't really a philosopher. So he was a mathematician trained by Emil Post and Alonzo Church at Princeton, and then taught at NYU for a long time. But he and the next guy, Hilary Putnam, who was a philosopher, possibly the second, well, maybe, I don't know, this contemporaneous with, like, he was a little younger than Quine. Both of them taught at Harvard, and there are theories named after the both of them. So he was also a very influential American mid-20th century philosopher. He studied under one of the logical empiricists, Hans Reichenbach, who taught at Harvard for a while. And so Davis was a postdoc at Princeton, and Putnam had his first job at Princeton. They became friends, and they rented a cottage in upstate New York in the summer of '57 and '58. And they thought, well, you know, let's think about logic together. And then they looked for some money, right? And they missed the funding deadline, so they approached the NSA, and the NSA gave them money to think about logic, but said, don't tell anyone who you got this money from. We're a secret. And then I think in '58 they got money from I don't know, the Navy or the Air Force or something like that. And these 2 summers were incredibly productive. So one of the things they did was come up with an efficient method for testing for propositional satisfiability, the Davis-Putnam procedure. And Davis then a few years later with 2 of his grad students amended that procedure. So building on that work with Putnam, came up with the Davis-Putnam Logeman-Loveland procedure, the DPLL procedure, which is basically now the core of all the sort of industrially applied propositional theorem provers, so-called SAT solvents that are used all over the place. And then the third philosopher is John Allen Robinson. He got his PhD in Princeton under Carl Gustav Hempel, who was also a logical positivist. And he also followed Quine's idea to use Herman's theorem to come up with a proof procedure that's easily implementable by a computer. And he called that the resolution method. And the resolution method then became basically the standard for how computer scientists were doing automated inference for the next 30 or 40 years. It provided also the groundwork for logic programming. So basically the Prolog programming language is an automated theorem prover using the resolution method. State-of-the-art provers. So Vampire is probably the one, Vampire is the one that wins all the prover competitions, right? So there's annual prover competitions at automated theorem, automated reasoning conferences, and Vampire uses resolution. And it's what powers the kinds of inference from knowledge bases like SNOMED-CT and the web ontology languages and stuff like that. The 2 people here are 2 of the main developers of Vampire. Laura Kovac on the right is one of the leading a group at the TU Vienna who's working on that, and the guy on the left is Vampire. Is Russian, and now I can only think of Sergei Achyutin. The other, it'll come to me. But you have all probably used a different piece of software that he invented. He's the guy behind EasyChair. EasyChair. Is conference management software. EasyChair. Let's get it. So everyone, like all the computer science conferences. Okay, second example, automated verification. So inference from knowledge bases is one thing, right? But there's a bunch of other things that computer scientists would like to prove things about. in a sort of a very general way, right? So for instance, about pieces about algorithms or pieces of software, they would like to know that they don't crash, they don't they can't get into infinite loops. There's things called protocols, right? So protocols are basically specifications about how different systems are supposed to communicate or deal with access to various pieces of various types of resources, right? So communication protocols like HTTP, for instance, is a protocol that dictates how computers are supposed to exchange, web traffic, right? So I'm asking for a web page, and then the web server is supposed to send me the web page, and what has to happen in order for that to work, right? And we would like to know that that all the web server doesn't get stuck. It doesn't end up only serving web pages to one client and ignore all others. Things like that, right? Circuits, of course, right? So the integrated circuits in the circuit boards of our computers, right? They all are supposed to behave a certain way, and we would like to know that they actually do behave the way that we intend them to. And there's basically two ways of making sure. The first one is to actually build the thing and run it and see what happens, right? A probably better and cheaper way is to not build it, but verify that the specification that we have designed, right? So that the design of the thing does the thing that we want it to do, right? I mean, that has sort of been a dream of computer scientists for a long time, sort of in the 1970s, right? They wanted to verify that that specific programs halt, or that they have the right that they exemplify the right behavior. And it was very difficult to even sort of make headway in like how do we even start doing that. Of course, it also suffers from the problem that the problem itself is very complex. Sort of the state space can get very large. But people eventually develop methods. Turns out that they used ideas that philosophers developed. I will show you in a second. And then computers also became more powerful. And then it became also very acute because it turned out that building the things and just running it for a long time and making sure that nothing bad happens actually can have very catastrophic consequences. And two famous examples from the 90s is the Intel Pentium floating point chip, which shipped with a bug and had to be recalled, costing Intel millions of dollars. And the second one was the explosion of the Ariane 5 rocket that also was where a software bug was responsible for that, right? So they on the maiden flight, the thing just exploded on the launch pad. So so people got more and more interested in actually coming up with industrial strength automated verification methods, right? So let me give you an example here of a very simple protocol, right? It's a protocol. It's not just simple, but it's also simple-minded. Like no one would want to use this protocol, but it's basically a protocol where you have one resource. And you have two agents, let's say processes that want to access the resource, right? A protocol, for instance, would generally say would generally specify how accessing the resource works, right? So, for instance, the agent can just not care about the resource, then it's neutral, or it can request the resource, and then it can get access to the resource and then do something with it, and then eventually it will release the resource again, right? And the protocol is supposed to have certain properties, right? So for instance, you want the protocol to be fair. You want it to be impossible that only one of the agents ever gets access to the resource and the other agent never gets access to the resource, right? So that's a fairness property, right? You also want the protocol to never deadlock, right? So you never want to be in a position where for instance, both agents have access to the resource, because that's bad. That's why you have an access protocol in the first place. You have a resource, and only one person is supposed to print to that printer or write to that drive or something like that, right? If two processes write to the same drive at the same time, bad things happen, and we want to avoid that. That's why we have protocols in the first place, right? And so protocols are described or specified using diagrams like this. It's called a finite state diagram. That sort of lists all the possible states that the system can be in, right? So it's the neutral state is the one in the middle, where both agents are neutral, and 1 and 2, thinking of these as propositional variables that encode the state of the system. And 1 says agent 1 is neutral, and 2 says agent 2 is neutral. And then one of 3 things can happen. Either the agents just do their own thing, and ignore the resource, or they request the resource. One of the 2 requests the resource. And then if N1 requests the resource, then I'm going to state S2. So R1 is now true. Agent 1 has requested the resource. N2 is still true. Agent 2 is still ignoring the resource. And once R1 is true, so agent 1 has requested the resource, then in the next step, agent 1 will get access to the resource, and then they will relinquish access to the resource again and go back to the start state. And on the right side, the same kind of thing can happen, except with the other agent. So agent 2 requests the resource, agent 2 gets access to the resource, agent 2 relinquishes the resource, right? So simple-minded protocol, right? Because I mean, at the very least, in real life situations, at least both agents should be able to request the resource at the same time, right? This protocol does not allow that, right? So that's why it's simple-minded. Right? So that this is an actual protocol would allow the agents to request the resource at the same time, and then it would say, well, which agent actually does get access to the resource, and it would have to remember that the other agent has also requested the resource, and then give access to the resource later, right? And when it gets more complicated like that, then you're more likely to get into deadlock situations or fairness considerations, right? But those are the kinds of things that you would like to verify about a simple protocol or a protocol like that, right? Can agent I always eventually access the resource if agent I requests it, right? So that's a liveness property. Do both agents ever access? Can it happen that both agents access to the resource at the same time, right? So that's a deadlock property that we want to avoid, and so on. Okay, so if you are a logician or a philosopher, then this will kind of seem familiar to you. It looks like a Kripke structure for modal logic. And that's exactly how computer scientists deal with these kinds of problems nowadays, right? So how did that become possible, right? So a computer scientist, Amir Noeli, who is on the next slide, in 1977 had the idea of taking the work of philosophers that philosophers had developed in the 20 years before that, and apply it to cases like this. And some of the people who were instrumental in bringing modal logic to the kind of maturity, to the kind of develop the foundations of those systems were the 3 that you see up here. The first one is Rudolf Carnap. He was also an influential philosopher of the 20th century. He was a central member of the Vienna Circle of Logical Empiricists. You've heard of some of the names of the other members of the circle already, right? So Hempel was one of them. He was the guy who taught Robinson, who came up with resolution. Reichenbach was not technically a member of the circle, but he had his own logical empiricist group of philosophers at the University of Berlin, and he was Hilary Putnam's supervisor. Quine visited the Vienna Circle in the early 1930s. Other people who were working in the Vienna Circle that you might know, Kurt Gödel, I already mentioned. Hans Hahn was an important mathematician working in Vienna at the time. Otto Neurath, who was a philosopher of science and invented infographics. the isotype system of visual communication, which basically looks like infographics nowadays. Anyway, so Carnap was a central member of the circle, was good friends with Alfred Tarski, good friends with Quine as well. And he, in the 1940s, in a series of books, laid out sort of the logical foundation of modal logic. So what's modal logic? It's basically an extension of propositional logic with some new operators. In the case of basic modal logic, typically we use a box and a diamond. And so if P is a proposition, then box P means that P is not only true, but necessarily true. Couldn't have been false. And diamond P means that P is possibly true. So P needn't be actually true, but it might have been true. Right? So he introduced this language. He introduced, had some ideas about how to go about doing proof systems for these systems, semantics for these systems. But the person who actually basically put all the things together and gave a semantics for modal logic was Saul Kripke, another hugely important American philosopher of the 20th century. And I give you a picture of him as a teenager because that's how old he was when he invented Kripke semantics for modal logic and proved completeness for it. He was 18 when he did that. Allegedly, he got a job offer from Harvard, which he answered by saying, "I'm very flattered, but my mom thinks I should finish high school." So he developed semantics for modal logic in 1958, and that basically started like revolutionized the field of modal logic. Lots of different philosophers, very famous names, famous for philosophers, obviously, were interested in modal logics, developed different kinds of modal logics, developed the meta theory of modal logics, developed proof systems for modal logics, et cetera, et cetera. One of them was the New Zealand philosopher Arthur Pryor, who applied the same ideas that Kripke and Carnap had applied to modality, possibility, and necessity to time. And he introduced operators G for globally true. G of P means P is always true. And FP for finally. So FP means P will eventually become true. Right? It might not be true now, but it will be true at some point in the future. Right? So these are the ideas that then Amir Pnueli in 1977 used to introduce a language that can reason about the behavior of protocols or finite state machines in general. And he called it linear temporal logic. And it allows you to formalize the kinds of properties that you would like to verify about protocols. For instance, the first property, is it true that agent one, whenever agent one requests the resource, agent one will eventually have access to the resource, can be formalized in linear temporal logic, right? So we want to say it's always the case that G, globally, if agent one requests the resource, R1, then finally, eventually, agent one will have access to the resource, right? So globally, if R1, then finally A1. And the second property, that there should be no deadlock, can be formalized as it's globally true that not A1 and A2, right? A1 and A2 is deadlock. Both A1 and A2 have access to the resource. We want to say that that never happens. So we say not that, and moreover, always not that, right? In other words, never A1 and A2, right? Right, so this is, right, so I mentioned here that he won the Turing Award for this work in 1996, just to indicate that this is not some niche interest among computer scientists. The Turing Award is basically the Nobel Prize of computer science, and Pnueli won it for linear temporal logic. And just a few years later, the American computer scientist Edmund Clark extended Pnueli's work from linear temporal logic to something called computational tree logic, which is even more expressive. and you can describe the behavior of more protocols and systems and circuits and so on. And he also came up, Clark did, with efficient methods for actually checking whether a protocol described by a finite state diagram, for instance, has the kinds of properties that you can formalize in this model, language of CTL or linear temporal logic LTL. And that's called model checking. And it's a hugely successful research project, also won the Turing Award in 2007. And just to bring it back home to our first example, one of the methods that is used to actually, in practice, test whether these properties hold is to use SAT solvers for propositional logic, which, remember, use the DPLL algorithm that was first developed by Davis and Putnam in 1958 in their summer in the Hamptons. All right, so those are my two examples. What should you take away from this? Logic is hugely important in computer science, not just theoretically, but there are industrial applications that are used all over the place to verify circuits, to verify specifications, to make sure rockets don't explode on the launch pad anymore, right? And the development of the fundamental methods that are used in these industrial systems go back to the work of philosophers who were obviously interested in all of these things, not for these industrial applications, but for philosophical reasons. So, in other words, you never know how things that you're interested in for purely large pour large, basically, right? So things that you're interested in for metaphysical reasons. 20 years down the road, someone might pick it up and say, "Oh, let's make sure that these integrated circuits work." Right? And I guess one thing that I also want to mention is that this cross-disciplinary connection between computer science and logic, and philosophical logicians in particular, is still sort of an ongoing thing, right? Like philosophical logicians and computer scientists, they all sort of keep on developing new extensions, new variants, new proof systems for all of these things, and who knows, maybe in 10 years, someone who's working on the logic of obligation, let's say, right, what ought to be the case or what must be the case, right, maybe has applications in AI or something like that, right? Thank you.
Any questions or comments for Richard?
Yeah.
So while a lot of this development in computing and logic was going on, there was also, just checking the timeline, there would have been parallel developments in quantum computing. Right. And so I was wondering if you know anything about like how quantum computing, the rise of quantum computing, quantum information changed the kind of logic you needed to deal with that kind of stuff. Because like you kind of lose this idea of things being either true or false, right?
Right. Funny you should mention that. Putnam was one of the people who worked on quantum logic, which is something that I think von Neumann first introduced in the 30s. But I think that's all I got for that, right? So I don't know when quantum computing itself actually sort of started. My guess is it's
Like
only the 90s, right?
Late 20s.
So Richard, isn't it striking that quantum logic hasn't had the ongoing unlike temporal or modal? I mean, it just seems to be a
Well, it seems to me that more people are getting more interested in it again. Maybe not necessarily for applications to quantum stuff, but for the properties that it has, namely that it's not distributive. So non-distributive logics are a thing currently, but yeah. I mean, I don't know. I don't know enough about quantum computing. My sense was always that it was basically you could deal with quantum phenomena in two ways. One is you could change your logic. Two is you could describe it sarcastically as but using a classical underlying classical logic, right? So if you're doing a theory of quantum phenomena, right? Like one thing is to change your logic, and the other one is to not change your logic, but to describe the statistical behavior of the systems. But yeah, more questions?
You said that early on, people were able to make programs to prove mathematical theorems from the Principia Mathematica, but do you know if there have been any cases of machines discovering novel theorems that weren't already known?
I think actually, yes, there aren't any. There aren't any terribly striking results in that regard. I do know that Newell and Simon, like their prover, prove a tautology that is not. It proved something about the system of Principia Mathematica, but this was in '58, and in '58 Russell was no longer interested in logic. Like he was interested in nuclear disarmament and wrote books like Why I'm Not a Christian and Why Marriage is Bad and stuff like that, right? So so when they wrote to him, he wasn't terribly receptive at that point. But there was a lot of development of theorem provers and applications to algebra in the '70s, and I think there were some. I forget which conjectures, but there were some algebraic conjectures that were proved with the help of resolution provers. And I don't know to what degree resolution provers are used in automated in current proof of systems. I think they use sort of a different method of proof search, which incidentally was pioneered by another student of mine, Wan. Also in the 1950s, the first proof search prover implemented on an IBM 305, I think, something like that. One of the first mainframes. Yeah, I wish like I should have it. Like yes, prove this so and so conjecture and blah blah. I think what they're useful for is like to fill in easy steps in logical inference in automated in computer system proof systems.